In this short lesson, I just want to define wave velocity. The velocity of the disturbance, the traveling disturbance, okay, along the medium, and also the velocity of the medium itself, and kind of distinguish those. So let's do that. It shouldn't take us very long. We know that periodic waves just means that they're continuously produced. It's not a pulse. And they travel along the medium. Now, velocity, v, is just distance over time. The distance that a wave moves, just like when we're doing circular motion, you know, to analyze the motion of an object in a circle, you consider the circumference, the 2 pi r, the distance, divided by the time it takes to do that, which is 1 period. Same idea here, but in this case, the distance is not time to go in a circle, but time for one cycle or oscillation. So d over t is the wavelength over the period, which is denoted as lambda over capital T. So that's the velocity. All right, and I'm just separating out the 1 over t there because we just learned in the last lesson that 1 over t is equivalent to, that's right, frequency. So F lambda. The period t is time for one event to occur, seconds per cycle. The frequency is number of events in a given time, so cycles per second. So they're inverses. Yep, they're inverses. All right. So here we have an illustration then of a transverse wave propagating, moving along, and it continues to do this. So this point here is at t is equal to 0, and I want to see what subsequently happens. Well, we have the ongoing periodic wave, but after a little bit of time, it continues to go. So there it is. I'm drawing one more cycle. So this time from t is equal to 0, if this is t is equal to 0, the time to do one more wave is the period. 1 period. And of course, the distance that the disturbance moves is 1 wavelength. That's lambda. All right. And so the relationship is that the velocity, could just say speed here, is f lambda, the frequency times lambda, or 1 over t lambda, lambda over t. So we have that frequency has the dimensions of inverse seconds, 1 over seconds. Lambda is meters, and we get meters per second. Yay! All right. The pulse, very similar. It's just a single disturbance in a medium. A single pulse traveling along. There it is. Boop! And this pulse just continues to move along the medium instead of this continuous sine wave of a periodic wave. All right. Traveling wave is just the regular periodic wave or disturbance traveling through a medium. So a little bit redundant perhaps. Hope you get the idea. And now the medium velocity. The medium itself. Not the wave velocity, but the medium velocity. In other words, what's the medium doing? So I'm going to show different pulses here. I got a pulse moving this way, another one here, and another one going the opposite way. It's all the same idea. In a little time later, we have that pulse that's traveling, displacing the medium according to the dotted line. The dotted line. And so really what the medium had to do is go from where it was to where it is. And it's moving transverse to the wave, perpendicular. So the medium just goes from here to boop, down to there. And we can show this at a bunch of different places. There it is, there it is, there it is. Okay, so this is what the medium is doing. It's moving vertically. So I'm showing the displacement in these little illustrations here. The displacement of the medium from where it was to where it is. All right, and so those little blue arrows are denoting the distance that the medium has to move in the amount of time it takes for the pulse to go from where it was to where it is. So there's a little bit of time to move like this. This is the distance the medium has to move. Okay, that's what's going on. And over here, same idea. A little bit redundant, perhaps. Make sense? That's what the medium is doing. Now, because that's kind of like it is a certain interval of time, and this is showing the distance, there is a medium velocity. And it turns out the medium velocity is greatest, like this medium velocity is greater here than it is here. See how it's moving further in the same amount of time? And the same thing here with a traveling wave. There it is, a moment later, whatever that moment is. And so we have the medium moving like this. Yes. Isn't that fun to follow? Of course it is. There it is. Okay, I don't have them all in there. Don't need them all. And some observations that we might make are, in addition to the fact that the medium is moving fastest in the location where, you know, it has to go the furthest, the acceleration of the medium is at where it's changing its motion the greatest is actually proportional to the displacement of the medium. So it's actually accelerating the greatest up at the peak, where the motion is changing the fastest. And right at the peak itself, it's not moving at all for an instantaneous moment in time. It's not even moving. But then the subsequent reality is that it does move because it's accelerating. And then it speeds up even though the acceleration is slowing down. But the different distances that it's moving are shown again by the length of the little arrows, the vertical displacement arrows. And of course also it's important to keep in mind that the medium velocity, how does it relate to the wave velocity? Well, certainly not the same thing. Why? Well, they are perpendicular to each other. If they're perpendicular to each other, they certainly can't be the same thing. They're different motions completely. Now, since my first video was about 15 minutes, this one hopefully is about 5, so that averages to about 10. We'll sign off here and pick it up again in the next lesson.